Right now, beneath the African continent, there's enough trapped heat to power every volcano on Earth for the next 10 million years. Meanwhile, on the opposite side of the planet, the Pacific Ocean floor is acting like a massive heat sink, draining thermal energy from Earth's core faster than anywhere else. This shouldn't be possible. A spinning sphere cooling in space should lose heat evenly, symmetrically, predictably. But our planet broke that rule 4 billion years ago and never looked back. The result is a thermal civil war playing out in slow motion, deep beneath the crust. And the casualties? They're mountain ranges, volcanic chains, splitting continents. This is the story of how Earth became the most lopsided planet in the solar system, and why that imbalance is the hidden architect of everything happening on the surface. Let's rewind to the beginning. When Earth formed 4.5 billion years ago, it wasn't the temperate, life-bearing world we know today. It was a hellscape, a molten sphere of liquid rock with surface temperatures exceeding 1200 degrees Celsius. The entire planet glowed like a newborn star, radiating heat into the frozen vacuum of space. And then, something remarkable happened. Earth began to cool, slowly, unevenly, chaotically. You'd think that a spinning sphere cooling in space would do so uniformly, like a hot cup of coffee cooling on a table. Same temperature drop everywhere, predictable, symmetrical. But Earth didn't get that memo. Instead, it developed what scientists now call hemispheric dichotomy, a fancy term for an incredibly lopsided cooling system. On one side, you have the Pacific Hemisphere, a vast expanse dominated by ocean, thin crust, and ancient cold slabs of rock plunging into the mantle. It's a thermal exhaust port, bleeding heat into space like a planetary radiator, running at maximum capacity. On the other side, the African Hemisphere, crowned by a massive supercontinent, thick, continental crust, and something truly bizarre lurking in the deep mantle. It's a heat trap, a thermal blanket, and it's changing the rules of planetary physics. So what's actually happening down there? 2,900 kilometers beneath Africa and the South Pacific lies the core-mantle boundary, the border between Earth's liquid iron core and the semi-solid rock mantle above it. This should be a relatively smooth transition zone, a predictable gradient of heat and pressure. But seismic waves tell a different story. When earthquakes send shock waves rippling through the planet, seismologists can track how those waves travel. And what they've discovered is shocking. There are two continent-sized blobs of anomalous material sitting on the core-mantle boundary. They're called large low-shear velocity provinces, LLS, VPS for short, but their nickname is far more evocative, the superplumes. One sits beneath Africa, the other beneath the Pacific, and they're fundamentally different from the surrounding mantle in almost every measurable way. These aren't just hotspots, they're massive, each one roughly the size of a continent and hundreds of kilometers thick. They're hotter than the surrounding mantle by several hundred degrees. They're chemically distinct, possibly containing material left over from Earth's earliest days. And most importantly, they're controlling how heat escapes from our planet's interior. Think of Earth's mantle as a slow-motion ocean of rock, constantly churning in vast convection currents. Hot material rises, cools, and sinks back down, like a lava lamp operating over millions of years. These superplumes disrupt that flow. They anchor themselves to the core-mantle boundary and force rising heat to find detours, creating pathways that concentrate thermal energy in specific regions. The result? Earth doesn't cool evenly, not even close. Let's start with the Pacific Hemisphere, Earth's cooling champion. The Pacific Ocean. Basin is the largest single feature on our planet's surface, covering more than 60 million square miles. But size isn't what makes it special. What matters is what's happening underneath. The Pacific is ringed by subduction zones, places where old, cold oceanic crust is diving back into the mantle at a rate of several centimeters per year. These slabs of lithosphere have been cooling at the surface for millions of years. And when they sink, they carry that coldness with them like refrigerated conveyor belts, descending into the deep. This creates what geophysicists call a slab graveyard, an accumulation of cold, dense rock piled up on the core-mantle boundary. It's the most efficient heat extraction system on the planet. These slabs act like radiator fins, pulling heat from the core and channeling it upward through the mantle, where it eventually escapes into the oceans and atmosphere above. The evidence is everywhere. The Ring of Fire, that horseshoe of volcanoes encircling the Pacific, isn't random. It's the surface expression of this massive subduction machine. Every earthquake in Japan, every volcanic eruption in Indonesia, every tsunami in Chile is connected to this hemisphere-scale cooling system. The Pacific is bleeding heat, it's working overtime, and it's dramatically outpacing the other side of the planet. Now flip to the African hemisphere, and you'll find the complete opposite scenario. Africa sits at the center of what was once Pangaea, the last supercontinent. When Pangaea broke apart 200 million years ago, Africa ended up surrounded by slow-spreading mid-ocean ridges. Translation: very little subduction, very few cold slabs, very little heat extraction. Instead, Africa has become a heat accumulator. Beneath the continent lies one of those massive superplumes we discussed, the African superplume. It's hotter, larger, and more thermally insulated than almost anywhere else on Earth. The thick continental crust above it acts like a ceramic lid on a pressure cooker, trapping heat that would otherwise escape into the ocean. But here's where it gets really interesting. That trapped heat is trying to escape, and it's succeeding in the most dramatic way possible. Rising from the African superplume is a network of mantle plumes, narrow columns of superheated rock ascending through the mantle like thermal missiles. When they reach the surface, they create hotspot volcanoes and volcanic provinces. The Afar region in Ethiopia, one of the most volcanically active places on Earth. The Cameroon volcanic line stretching across Central Africa. The East African Rift System, where the continent is literally tearing itself apart. That rift is the key. Right now, Africa is splitting into two pieces along a 4,000-kilometer crack that runs from the Red Sea to Mozambique. In 10 million years, there will be a new ocean between East Africa and the rest of the continent. This isn't speculation, it's inevitable, and it's being driven entirely by that trapped heat desperately trying to escape. The African hemisphere isn't just retaining heat, it's building pressure. And that pressure has to go somewhere. This hemispheric imbalance isn't some academic curiosity buried in geology papers. It has real, measurable effects on our planet's behavior. First, plate tectonics. The asymmetric cooling creates asymmetric forces in the mantle, which generates asymmetric patterns of plate motion. It's why the Pacific plates are moving faster than the Atlantic plates. It's why subduction zones concentrate on one side of the planet, while rifts concentrate on the other. Second, volcanic activity. The distribution of volcanoes across Earth's surface isn't random. It directly reflects this thermal asymmetry. The Ring of Fire exists because of Pacific subduction. The African rifts exist because of trapped continental heat. Two sides of the same planetary coin. Third, Earth's magnetic field. The core's heat flow influences convection patterns in the liquid iron outer core. the engine that generates our protective magnetic shield. Asymmetric cooling might contribute to anomalies in the magnetic field, including the South Atlantic anomaly, where the field is unusually weak. And finally, the long-term evolution of our planet. Earth's cooling rate determines how long plate tectonics can continue, which determines how long our planet can maintain a stable climate, which determines how long life as we know it can persist. This isn't happening on human timescales, but it's happening. Here's what keeps geophysicists awake at night. We still don't fully understand why these superplumes exist or how they formed. Are they remnants of the magma ocean that covered early Earth? Are they chemically distinct blobs that have persisted for billions of years? Are they actively fed by heat from the core, or are they slowly depleting? And perhaps most intriguingly, are they permanent features? Or do they migrate over geological time? Some evidence suggests these thermal anomalies might have moved in the past, that hundreds of millions of years ago, the hemispheric asymmetry might have looked different. If true, that means Earth's cooling pattern isn't fixed. It evolves, it migrates, it reorganizes itself on timescales we can barely comprehend. This raises a profound question. What happens when a planet cools unevenly for billions of years? Does it eventually stabilize? Or does the asymmetry grow more extreme until something breaks? We're watching that experiment unfold in real time. We're living on a planet conducting a 4 billion-year test of thermal dynamics at planetary scales. So the next time you look at an image of Earth from space, that perfect blue sphere floating in darkness, remember what lies beneath. Remember the lopsided heat flow. Remember the superplumes and the slab graveyards. Remember that one hemisphere is desperately trying to cool, while the other traps heat like a planetary fever. We live on a world in thermal disequilibrium, a planet divided against itself in the slowest, most majestic way possible. And that asymmetry, that fundamental imbalance, buried beneath thousands of kilometers of rock, is what makes earthquakes shake, volcanoes erupt, and continents split. Earth isn't perfect. It's not balanced. It's beautifully, catastrophically lopsided. And that's exactly what makes it alive.